Hello everyone and welcome to this lecture about why we visualize. This is just an introduction to the question of visualization for people who have never been doing visualization for a living and just have to do it sometimes. By visualization I mean data visualization. So the bare minimum you need to know about visualizing your data. The program for these slides, I'm going to address first the question of the framing power of visualization, why visualizing helps you find new insights, what's the difference between exploration and confirmation using statistics, and then what is the difference between exploration and explanation. And finally, I will make a short point about why a hypothesis is a liability. You will understand that as we go through those slides. I'm going to state right now what the takeaways are, and we will come back to them in a more precise way in the end, obviously. First, visualization is not neutral. It's not about faithfully representing the truth as it is, even though you don't want to lie. But there are always trade-offs and things you have to hide in order to make other things visible. The strength, the value of visualization lies in the fact that it can show the unexpected. Exploration does not always require a message to communicate, which makes it different from traditional visual communication. And that is essentially because when you explore, you visualize for yourself, which works differently from visualizing for others. And that's something that you have to know in order to not make some very common mistakes. Let's start with what I call the framing power of visualization. The way we represent data visually shapes how we frame and understand the issue at hand. So what I call here the issue at hand is whatever you visualize your data for. You always have a reason, a motivation, you want to understand something, you want to potentially communicate something. And so it's not just about the data, it's about the context, it's about, the people, the things that your data is about. Let me just give you an example of this framing power, actually 3 examples that I get from Sophie Burgos-Thorsen, from her PhD thesis, and these examples are about how to govern cities. My first example is with one of the most common forms of visualization or data visualization, which is cartography. In the late 19th century, Charles Booth created the poverty map of London, basically plotting where poor people would be living and making some, structuralist points about the fact that poverty is not just about your individual choices in life and so on. It's not just your thing, but it's also a collective thing. It's also about the system, about society and so on. And therefore, it is something you can act on. So his maps have been known for reframing the question of poverty in a way that would appear as a manageable problem to policymakers. And this has actually led to a change in the mentality of how we manage poverty and so on. So you might say kind of a positive example of the framing power of visualization. Second example, not really data visualization, but more like visual communication. Those are about camera pictures of people living in poor conditions. So poor people and their complicated conditions of existence that might not be visible to people who would never go to those places, and that they have been about the same times made visible by Jacob Riis in New York, for example. And this has helped convey this idea that we have to act on poverty and so on. So also, maybe the thing that is important to highlight here is that the picture is easy to circulate You can't move the conditions of existence of people living in poverty to other places, but you can move the pictures. So the pictures are what Latour calls immutable mobiles. Basically, they can go to other places without changing. And there's a lot of power in this. And through this power, you can make some changes by making certain things visible to certain people. My third example is a negative example, an example of visualization used to harm. And those are the infamous red line maps made in a number of cities across the USA in the 1930s. Basically, the idea was to make it more difficult for people of color to get loans. And this was done through policy making, but in a way that was not very explicit. So that was hidden in a way, and it was hidden in maps that were existing as visualization, like cadastral maps. Basically, those maps would tell you that in some areas, the rate to get good loans, you have to pay more to get a loan, and in other areas, you have better loans. And of course, the loans that would be unfavorable would be where people of color live. But you would not have to say it explicitly. It could just be the map that is designed this way through, a process that you don't know about. Basically, what you have to retain here is that the visualization has been used to hide rather than to make explicit this discrimination, this segregation. And it took a lot of work to actually make those maps visible, which has been done, of course, since. So now that we know that there is a lot of power potentially within data visualization, let's move to why we want to use visualization to engage with our own data. Where I'm going here is that I am assuming that you will be visualizing because you have data to explore. So how do you find new insights? First, let's establish that there is value in visualization. Galileo used to visualize, for example. You see right now the pictures that he drew manually after his observations of the moon. So a lot of work, and this has scientific value. This is kind of a measurement, if you want. The thing that specifically he were to make visible in those drawings was the fact that when the light comes in a very tangential way to the surface of the moon, you see the shapes of those shadows, which tell you that actually the moon has an accidented surface. It's not just a perfect sphere that is painted with shades of gray. It's actually a landscape with mountains and valleys and so on, or seas, as we call them. And therefore, this might be a celestial body that is similar to the Earth and so on. So that's the point of making those pictures, and that's why they are related to measurements. They are kind of measurements. And here is a more recent example. In the 1964, the USA sent the probe Mariner 4 on the surface of Mars. So 1960 is old. This is a digital camera picture. Basically, you understand what it is because you have a smartphone and you took those pictures. But just think of the state of the technology in 1964. And even before, because you had to make the camera on the probe before you send it, and then it takes years to go there. So what I want to say here is this is a very primitive, very low resolution picture of the surface of Mars sent by Mariner 4, and the transmission rate is so low that basically they receive a pixel once in a while, and then they draw that pixel when it arrives on the wall. So you see here the person basically manually enacting the picture by translating the codes into RGB hues and shades, and then paint them literally with paint on the wall. You would not go through that amount of effort if it was not worth it. That's the point that I want to make. Visualization is sometimes critical, and so critical that you would spend literal millions for seeing certain things. That's because they are, in some sense, measurements. Okay, so maybe I've convinced you, or maybe you knew already that visualization has some value. But what value? What makes that picture or any other visualization valuable? The way we usually make this point is by using the Anscombe quartet. That's what you're seeing in this slide right now. So the Anscombe quartet is a fabricated data set by this guy named Anscombe. And the pictures you will see about the Anscombe quartet, they just come from Wikipedia. So if you want to know more about that, just look at the Wikipedia article. But I'm going to give you the gist of this. So the Anscombe quartet is composed of 4 series that you see, 1, 2, 3, 4 on this table. And each series has the same number of data points, 11, I guess. And each series is composed similarly of 2 dimensions that are the same for each data point, so X and Y. Each series has the same dimensions. And they don't represent anything in particular because it's a fictitious data set made to make a demonstration that I'm going to go through. But just to help you think of this in a more practical way, I'm going to give you an example of what it could be. So you could have 4 groups of people. So each data point would be a person. X could be one quantitative measure and Y another quantitative measure, say your height and your income. And then you would have 4 series because you would have 4 groups. So maybe 4 groups of 11 people who live in 4 different cities. And you may have questions such as, is it different? Is your height different depending on where city you live in? Is your income different depending on the city you live in? So you would try to contrast the groups 1, 2, 3, 4, depending on one, either, both of those variables. Right? Because, for example, you would expect that people have the same average height in different cities, if they are in the same country at least, but maybe very different incomes. Okay. So if you want to do this, you can use the classic statistical toolbox. And you could, for example, look at the average income or the average whatever. So if you do this with this quartet, which is what makes it specific, you would realize that the 4 series are actually identical. So the average for dimension X is the same for the 4 series. The variance is the same. The average and variance for the Y dimension is the same. The correlation between X and Y is the same. The linear regression is the same. The coefficient of determination R squared is the same, and so on. So basically, it looks like they have the same profiles, like 4 different samples of maybe the same kind of data points. But if you actually visualize them, you realize that they are in fact very different. In fact, so different that they can tell kind of stories. You could spend some time to try to guess what those different stories are, try to invest some mental energy to understand what it could be. I'm just going to go through that. Basically, the first series is the only one that looks like a normal statistical data set, in the sense that it's like a cloud of dots that follows a certain trend. It's kind of random. While the second series looks like a perfect parabola. So this doesn't look like a random data set. But also, and more importantly, it's clearly not linear. It's quadratic. It follows a parabola. It kind of looks like someone throwing a ball that is going to be landing on the ground at some point. Third case, we still have something very following clearly a trend that is very linear, but just with one outlier. So if I had data like this, I would just double check that I don't have an issue in my measurements or in my processing, because this really looks like an anomaly that could be like a mistake or a bug. And final case, even weirder, we have a lot of data points that share the same value on X and just one massive outlier. But also, it's the only of those 4 dimensions where you have multiple points with the same X, so it looks like it's a completely different kind of thing. I just want to come back to the table now that we have seen that they look different, because you could think of this as a visualization. The table is in some way a visualization, and if you spend time with the data, you could see a number of things. I sometimes do that with my students when I am in person with them, And then the two things that are relatively easy to figure out is that the x-axis has only integers, so round numbers, while the y dimension has decimal numbers. So, for example, if if you have integers, it could be something like the number of kids, while income will probably not be an integer, or your height will not be an integer. So this could give you an idea of what it is. The other thing that people see quite often is the fact that for series number 4, you have all those data points sharing the value 8 for the x dimension. I'm just pointing this out to say you can see things if you spend time with the numbers, but certain things will remain very hidden. So that's when visualization is useful, but I should rather say depending on the kind of visualization you do, because the table is a visualization of some sort. But certain visualization give you visual affordances that are better for seeing certain things and worse for seeing other things. This is not the point of those slides, but in another set of slides, I will tell about how we make a visualization and what are the rules to navigate this situation. For now, the point I want to make is that there are certain things that you will only see if you do visualization, because you may not have the idea of making the statistical measurement that would reveal them. It's not that there is no statistical measurement to see what is going on in these different data sets, but rather that there are always statistical measurements that you will not do because you don't think of it. And that's where the question of the unexpected matters. The valuable property of visualization is that you don't have to think of it so that you see those things. I want to tell you briefly about this guy, John Tukey. He's a very famous mathematician and statistician. His most famous accomplishment, I believe, is his work on the fast Fourier transform, which is a very, very important technique that is used everywhere when it comes to measuring things and processing image and audio and all of that. If you don't know what that is, I'm not going to talk about it, but if you know what that is, you might be impressed by the importance of that guy if you don't know who he is. But he has also worked on what he calls exploratory data visualization. And I'm showing you this picture of him to say that this is a very serious guy. And the picture is even overdoing it. You have like the clock, time. You have a ledger or some book with numbers. You have the big computers, the glasses. The guy is not here to have a laugh with you and tell you a joke. He's like a worker. He's like an intellectual force. I say all of this because you may think that visualization is about making nice pictures with data. But in fact, very serious people have looked into the question of visualization because they had problems with this. And he did. Basically, Tukey thought that statistics are made so that you can confirm your hypothesis. This is as a way to support the hypothetico-deductive logic of reductionist science, right? And this is, just to be clear, this is all good. I'm not against doing this. We absolutely have to do it, but not all the time. And Tukey was observing that what people actually do with statistics is not really confirming hypotheses, but also finding hypotheses. And then he was like, oh, okay, we have a problem. Because obviously, if you then use the same tools to confirm your hypothesis as the tools you have used to find your hypothesis, then by design it's going to work. But this makes it depend in a weird way. It creates a weird dependency loop. You should make your science falsifiable, right? So you should not use the same tool to make your hypothesis as to confirm them. So basically, he defended the idea that if you want to explore your data, you should use different tools, which is the idea I want to convey here. He wrote this book, Exploratory Data Analysis. It's not just about visualization, just to be clear, it's also about statistics. So what I am contrasting here is exploratory statistics versus confirmatory statistics. But obviously, visualization is a very important part of the exploration toolkit. I'm just going to encapsulate that with 2 quotes from the book. The first one is the following: "The greatest value of a picture is when it forces us to notice what we never expected to see." What Tucky means here is that the virtue of the visualization is it can show you not only things that are unexpected, but even things that possibly you don't want to see. Not just that you don't think of looking for them, but potentially they annoy you. And that's a strength in a scientific setting, I think, and he does too, because your hypotheses are only as robust as they resist falsification, right? They resist people trying to prove that you're wrong, and you are ultimately right when your hypotheses are solid, right? So the way that visualization can make you vulnerable, right? They give you a chance to see that you've been wrong all along, and that's really a strength in a scientific setting. And here's the maybe deeper second quote: "Far better an approximate answer to the right question, which is often vague, than an exact answer to the wrong question, which can always be made precise." In this case, what we're talking about is the nature of important questions. Because maybe this is totally obvious, but the important questions are hard, or let's say the important questions that are easy to answer have been answered already. So only the difficult questions remain. And these questions are often difficult to answer because they are vague, and they are vague by nature of what we want to know about the world. So just to give you an example, if you have questions about are European democracies becoming weaker right now, or are they becoming stronger? The problem with this question is that it is vague in the sense that you would have to define what democracy is, what is a strong democracy, what is a weak democracy. People don't agree on what that means. This question is vague for those reasons. But it is also the question that is really important. While if you narrow down that question to a very specific and narrow version of what democracy is and a measurable form of strength and weakness, you will have to leave aside a lot of things that are actually important. So there is often a trade-off between what is important and what can be captured by rigorous measurements. And what Tucky says here is that the important things are the important questions. And if we have to give them a vague answer, that's better than nothing, because at least we would be answering the right questions. Because sometimes through the work of operationalizing something that can be measured exactly, we lose the meaning and the broadness, the breadth of what we want to understand. So that's where visualization is also important. It can give you a broader picture in a metaphorical and also very literal sense. Now let's look at an example of exploratory statistics versus confirmatory statistics following the idea of Tucky. Just to clarify what confirmatory statistics are. Basically, I'm talking about descriptive statistics, the average, the correlation, the kind of stuff that we have seen with the Anscombe quartet. I want to talk, for example, about the p-value. If you've seen economic papers or other pieces of work using these tools, you may know that the p-value is sometimes represented with these little stars, is a way to measure the statistical significance. If you have those little stars, if you have the p-value, it means you are in the world of confirmatory statistics. What they mean is that when they do these calculations about whatever this is about, I took that from a paper, 3 stars means you can really trust this number. 2 stars is like you can quite trust. And then if you don't have any stars, it's probably numbers you don't know if they are statistically significant, meaning maybe those numbers may arise by sheer randomness. But the ones that have the 3 stars those are very numbers that are very unlikely to have been just the fruit of chance. That's why you have here, the p-value. The smaller the p-value, the better. So that's why 3 stars is p below 0.001. This measurement of statistical significance has also been criticized a lot. I'm not going to go into that debate, but you just have on the right a screenshot from X Cassidy, a webcomic that is laughing at the things that academics say or write, or how they frame p-value when the p-value is not really good. And they would say stuff such as highly suggestive or significant at the p below 0.1 level. Whatever. It's just to say p-value has been criticized, which doesn't make it wrong per se, but just as any tool, it can be misused. So how to know if you are doing confirmatory statistics or exploratory statistics, or if you should go for one or the other? Basically, it's all about whether or not you have a hypothesis. If you have a hypothesis, I mean a very specific, narrow operational question, then you can just test it. If all you're interested in is testing a hypothesis, then just go for confirmatory statistics. They are made for that and all is good. If, on the other hand, you have a general question, but you don't know exactly how it could translate at the data level, then you don't have a hypothesis. And what you're looking for is a hypothesis that you could then go to test. If that's the case, then definitely you need to go for exploratory statistics, exploratory data visualization, data analysis, which means you will visualize your data in various ways. In short, you will explore when you are looking for questions, while you will use traditional statistics when you are looking for answers. And I get that in a real-world situation, very often we actually first we look for questions, and then down the line we have formed hypotheses, and then we would look for answers. Now I am going to contrast exploration with explanation. Notice the difference here. So exploratory visualization versus explanatory visualization, or in other words, traditional visual communication. The key thing here is, do you visualize for yourself or for others? You have here a simple example of what it is to try to explain through visual means. So this is data visualization for kids. There are multiple books. Those illustrations are made by Nicholas Blackman. And the first thing you will see is that you have illustrations in those pictures. Actually, they may look like illustrations to you. If you look closely, you will realize that in fact they are data visualizations, or they incorporate data visualizations. You have like a little bar chart here, you have diagrams, this is also like a bar chart, and so on. But the artist or the author has made an extra effort to make the points not only appealing, but also clear. So this is the logic of visual communication. You know what message you aim to convey, and you will optimize your graphic decisions so that the message can be conveyed in the most clear, faithful, and appealing way. Which is why we have this big whale, which is why a number of decisions. Those visualizations are breathing, they are not, they use appealing colors and so on and so forth. This works because the artist knows what the message to convey is. You see that all those pages have kind of a point. They are looking at something in particular. This is the very big difference between what happens when you visualize for yourself. Because when you explore data, and if you look for questions, then you don't really know what you're looking for. Because you're not looking for an answer, you're looking for a question. So you're giving yourself a chance to see the unexpected, but then you don't know what you should optimize your design for. So what you will do in those situations is that you will most often try many different things. So exploration is very iterative, and it often uses tools that work like platforms, where you can change the settings very often so that you can explore different facets of the data, make different associations, zoom in, zoom out, and go to different aspects of the data points, like filtering them and stuff like this. And you do this precisely because you don't have a message. So should you go for visual communication, or explanation, or should you go for exploration? Well, that depends on whether or not you have a message. If you do have a message, then definitely you should go the route of traditional visual communication and optimize for that message. If you don't have a message, you have to use the tools in a very different way to give yourself and your team a chance to see things. That's kind of a very different logic. This point is very important because most of the time you will use the same tools. So for confirmatory statistics versus exploratory statistics, Turkey's point was you should use different tools. Here the point is rather you will use the same tools, but you must be aware that you should use them in very different ways. Now I just want to make the point that a hypothesis is a liability. That's actually the title of a paper. I'm going to go through the paper with you. Very short paper, just to make one very specific point that will show you an example of what I've been trying to convey as a message in those slides. Just as a preamble to that paper, I want to show you a video. It's a video that went viral in the early 2000s. You can find it on YouTube. I'm just going to show it to you right now. The video is very short. It's like a minute and a half, and it's kind of like a little game. I am assuming that maybe you see this video, the video you are watching right now, my video, on a very big screen, and I want to show you this video on a smaller screen as you would have watched it in the 2000s. Because the size in this case is important. It's an attention test, and you will have to count something in this video. So I'm just going to play the video now.
This is a test of selective attention. Count how many times the players wearing white pass the basketball. How many passes did you count? The correct answer is 15 passes. But did you see the gorilla?
And you can go back to the video on YouTube and double check that this is not a trick. You actually have this gorilla going through the crowd, and basically if I ask you nothing, you will probably see the gorilla, but because you would be so focused on all of what is going on, and you would be so focused on who has a white t-shirt or a black t-shirt, that you would completely miss the gorilla. Some of you probably knew about this video, possibly all of you. It really depends because it went viral in the 2000s. So some people are also too young to have seen this video and don't remember it. This video was so famous that it has actually inspired the paper I want to talk about, and that explains why this paper has a gorilla. So this is a paper that describes a small experiment that will exemplify this question of attention when it comes to exploration. It's a teacher of exploratory data analysis. So the statistics, as Turkey defended, they should be when you need to explore. You have two data sets, men and women, about, so each data point is a different person, and you have the number of steps they walk every day and their body mass index. So you have the BMI and the number of steps. And if you plot them, you will see this on the right with the females in red and the male in green. Now, the teacher makes two groups of students that don't know about each other, like two different classes. The first, the teacher says, okay, you have two groups, men and women, and your hypothesis, your question is, does the body mass index correlate with the number of steps you walk every day? Does it correlate more for men than women, the other way around, or does it not matter? So the first group is called hypothesis focused because they have a very clear question to answer. And the second group, the teacher just gives the data sets and asks the students to find what's an insight to share. And the hypothesis focused group, most of the students did not discover the gorilla, while for the hypothesis free group, most of the students have discovered the gorilla. Why? Well, obviously, because if you have a hypothesis, you can just jump to making the test with traditional statistics without visualizing. And if you do that, you will not have a chance to see the gorilla. Obviously, the gorilla is completely unexpected because the data set has been fabricated to have this gorilla in it. So the point here is that you may think that a hypothesis is always more, gives you more chances to find interesting things. But what this shows is that having a hypothesis may actually show you less, because by jumping to answering that hypothesis, you will not give yourself the chance to see other things that maybe are even more important. And the classic thing that would be very important here is that your data has a big problem. If you don't visualize, you have one less chance to realize that you have a big problem with your data. That is why a hypothesis is a liability. Takeaways. First, visualization is not neutral. You always choose a frame that you convey through your visualization. You emphasize certain things and you de-emphasize others by the choices you make. And because of this, the visualization has a certain power that you must account for. Then the value of visualization in a setting like us is essentially that it gives ourselves a chance to see the unexpected, which is especially important if you want to go fast and if you are alone or in a small team. Because if you have many eyes on the same visualization, then people will have different ideas. But if you're alone, you need a way to give a chance to the unexpected to arise. And that's what visualization can do for you. So we would call that data exploration. And the specificity of data exploration and the problem to enact it is that you don't know what the message is. So because you don't know what the message is, you have to try different things, which makes exploration very iterative by nature. So you iterate through different visualizations to see different facets, and you would be engaging with your data this way so that the context, you learn the context by spending time with the data. So the context is in you. You, after a while, remember that you have picked that color for that category, that other color for that other category, that you use the x-axis most of the time for a certain attribute, and blah, 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 blah. So you will, in this process of exploring, you will make decisions for yourselves that you never have to explain to others. Then comes a problem with this, which is that at the moment, at the end of your work where you have to communicate on your data, you have to remember that all this context that is in you, you have to make it explicit. So typically the visualizations that are very clear to you are not clear to other people, which means that you will have to use the same tools, the visualization tools like Power BI or whatever, Excel, Tableau, Data Wrapper, same tools, but you will use them in a different way because now you know what kind of points you want to make. And to make those points most explicitly, what you will do is you will add a title, you will curate your visualization so that you emphasize the right things and you de-emphasize other things. You will add annotations, you will add a legend, you will add some text that explain what is going on and what is the point of the visualization. And all of that is stuff you don't do when you explore, but you have to do when you communicate your visualizations to an audience. How to do that? This is a point for another set of slides. Thank you.